Okay guys, I decided to make this video because quite a few people were saying they're having issues with transformations, dilations, etc. So what I wanted to do, depending on which method you use, I just wanted to show you how it works. So first off, what I'm going to start with is function notation. So if I say I want to dilate something from the x-axis, um, let's have a look. We'll say y equals x squared, most easiest graph. So y equals x squared. If I want to dilate it from the x-axis, that is a times f of x. So what we're doing is we are multiplying, f of x is our y values, we're multiplying all of our y values by a. Okay, so if we multiply all of our y values by a, that's a dilation factor a from the x-axis. Okay, now if you were to do it in mapping notation, if I'm dilating factor a from the x-axis, I would have my original points, and when my image points, if I'm multiplying all of my y values by a, my image points become x dash, and then a times y dash. So I've multiplied all of my y values by a, and if you think about it, if these are my y values, if I multiply them all by a, they're going to get further away if a is greater than 1, and they're going to get closer to the axis if a is between 0 and 1. So this is in function notation, the first one, the a times f of x, that's a dilation factor a from the x-axis. This is in, what do you call it, image notation, I guess you would say. So you're saying all of your x values, they stay the same, but your y values are multiplied by a. Now, in terms of a matrix, if we want to dilate by factor a from the x-axis, your matrix is x, y. This stays the same because this affects y values. And then this value down here, that would be a, that affects x values. Now I'll tell you why this occurs. Actually, yeah, okay. So what am I going to get? If we look here, if I multiply this out, if I said x dash y dash is equal to, I get x dash equals x, y dash equals a y. When I transpose them, I get x equals x dash, y equals y dash on a. Now, if I was to substitute them into our function up here, I would get y on a, or y dash on a, is equal to x squared. X dash squared, when I multiply the a across, I get y equals a x squared. So that is when I use matrix notation to dilate factor a from the x-axis. I have substituted in, and I get a times x squared, which we know from function notation. If we put an a out the front of x squared, we'd get y equals a x squared. Okay, in terms of mapping notation, we have x becomes x dash, x equals x dash, y equals ay dash. When we transpose them, we get x dash is equal to x, y dash is equal to y on a, and then we sub them into the equation, so we get y on a equals x squared, therefore y equals ax squared. So it gives us exactly the same thing. We want to get our image points by themselves, so that's why we transpose it. And then we sub them in and we get our dilation factor A from the x-axis. So that's from the x-axis, both in function notation, in image notation, and also in matrix notation. So if I want to dilate factor A from the x-axis, we could say A times f of x, or x, y goes to x dash, a, y dash. Well, actually, I think the notation I use is, let's have a look. I don't really ever do it this way. Transformations. Okay, so xy becomes x plus h, y plus k. Okay, so then we say xy becomes x ay. So therefore, our image x dash is equal to x, and y dash is equal to ay, and then we transpose them. Or we know in function notation, if we want to dilate from the x-axis, it's 1, 0, 0, a. So they're all dilations of factor a from the x-axis. Okay, now this is the one that seems to bugger everyone up. If I want to dilate factor a from the y-axis. So if you think if you're dilating from the y-axis, if I dilated factor 2 from the y-axis, I'm making everything get 2 times as far away from the x-axis, from the y-axis, sorry. Now if you had a point here 1, that point would now move out and become 2. So what I'm doing, I'm multiplying all of my x values by that value of a. So I want to dilate 2 from the x-axis, from the y-axis, sorry. I am going from x, y. I'm multiplying all of my x values by 2. So I get 2x, y. Because that's a dilation factor 2 from the y-axis to double all of your x values, so it'll spread everything out further. Okay, now let's have a look at this in terms of function notation, in terms of image equations. X dash would equal 2x, y dash would equal y, and then if I put it into our, transpose it first, x equals x dash on 2, y equals y dash. If we put it into our function notation, if we put it into a function, we would get, if we had y equals x squared again, that would become y equals y equals, and then we've got to replace x with x on 2. So x on 2 squared, which is y equals x squared on 4. So that's a dilation factor 2 from the y-axis. Now I'm going to show you graphically how it looks. Oops. So if we go in here, oops, if we have, let's define x squared. So x squared is defined as f of x. Now if we go into graph and table and we say f of x sketches our graph, and then if I say f of x on 2 and we sketch it, you can see our original x value there is 1, 1, but when I have x on 2, that's actually doubling all of the x values, because when you dilate from the y-axis, it's the reciprocal, 1 on. So here, this is a dilation factor 2 from the y-axis, because it's going from 1 out to 2. Okay, so that's in function notation. And that's, if I change this to be f of 2x, that's a dilation 1/2. So we would expect this value here, 1, 1, to move into a half one. So let's have a look. It moves into a half one. So when it's from the y-axis, it's the reciprocal. If I want to dilate factor 2 from the y-axis, then it's got to be 1/2. That dilates at factor 2. But if I want to dilate it a half from the y-axis, then it's got to be 2x, and it brings it in. Okay, so this is in this is showing it through image, like using image equations. In function notation, it's just f of x on a. So if I want to dilate 2 from the y-axis, that's the same as f of x on 2. So whatever that value is, it's the reciprocal. If that was 1 on a, sorry, if that was a half, if that was 1/2, then of course this would be 2x, because the reciprocal of a half is 2. Okay, so that's from the y-axis. Image equation, function notation. Now, the sort of funky thing about this is, if you want it from the y-axis, factor a, using matrices, it's the top left-hand value, but if it's a, you use a. It's not the reciprocal. The only time you use a reciprocal is if it's in function notation, and I just stuffed that up. So 0, 1, okay, xy, and I'm going to say that equals x dash y dash, just to show you what occurs here. So if I multiply this out, I get a times x equals x dash, and I get y equals y dash. When we transpose our equations, we get x dash equals, x equals, x dash on a, and y equals y dash. Nothing changes. So that means we replace our x's with x on a, and we replace our y's with just y. So if I had y equals x squared, I would get x on a squared, which is x squared on a. So if I want to dilate factor a from the y-axis, we know, I forgot the squared on the bottom, we know in function notation, it's f of x on a, and you can see here, this is the graph of f of x on a, because I've replaced x with x on a. So when you dilate from the y-axis, let's write down what we know. So we get f of, if I want to dilate by factor a from the y-axis, I get f of x on a. That's in function notation. Or in image notation, xy becomes, now remember, when we're from the y-axis, factor a, we're multiplying all of our x values by a, and our y values are staying the same. So then we would say x dash equals ax, y dash equals y, and then we get x equals x dash on a, y equals y dash, which is why those two things are the same. And then if we want it in matrix notation, if we're dilating from the y-axis, it becomes a, 0, 0, 1. So down here, that affects, is that affects or effects? So go with E. Affects x dilation, and then this affects y dilation. Okay, so that's our x and y dilations. The only other thing you can really do with these matrices is if you want to reflect it in the x-axis. So if you want to reflect in the x-axis, then you get 1, 0, 0, negative 1, because we know this value here is what affects x values. So if you put a negative there, it'll reflect it in the x-axis. If you want to reflect it in the y-axis, we're going to get negative 1, 0, 0, 1, because we know that's going to affect our y values. And likewise, if you had to do a question using the image stuff, if you're reflected in the x-axis, x, y, well, all of your y values become negative. So it's x, x, and negative y. So we're going to get x equals x dash, y, sorry, x dash equals x, y dash equals negative y. So we get x equals x dash, y equals negative y dash. And you can see that that's going to be a reflection. If I said negative y equals x squared, that's the same as y equals negative x squared, which is a reflection of the x-axis. It turns it upside down. If we did it in the y reflection, x, y becomes negative x, because I'm changing all of my x values from being positive to negative and negative to positive. So x becomes negative x. Y stays the same. So I get x dash is equal to negative x. Y dash is equal to y. So x equals negative x dash. Y equals negative y. Not negative y, just y. And if we put that into our equation y equals x squared, we get y equals negative x, because I'm replacing x's with negative x squared. So y equals x squared. So that's a reflection of the x-axis. That's a reflection of the y-axis. With the graph of x squared, it's exactly the same. And we know that, because when you're reflected in the y-axis, it becomes exactly the same graph. Okay, lastly, you've got translations. Most of you would already get this. F of x minus b translates right b units. If we think about it in terms of function notation, in terms of image equations, x, y. If I want to move all my x values to the right by b units, I become x plus b, because it moves every x value b units to the right, and y stays the same. Therefore, x dash is equal to x plus b, y dash is equal to y. From here, if we transpose it, we get x equals x dash minus b, y equals y dash. And you can see there, if I had y equals f of x, that would become y equals f of x minus b, which we know is a translation to the right of b units. And conversely, if it was a plus, then that translates it left b units, because this would become x minus b, because I'm moving all of my x values left b units. That would be a negative. That would become a positive, and this would become a positive, which we know is b units to the left. Okay, so that's translations left and right. And lastly, we've got translations. Oh, hang on. In terms of matrices, if I had 1, 0, 0, 1, x, y, if I want to move it right b units, then that will be a b. So it takes that value. So if I said, if I want to go right 5 units, then that'll be positive 5. And if I want to go up 6 units, we'll call that C. So that'll be plus 5 and plus 6. So they keep the sign of whichever way you want to go when it's in terms of matrices. Let's have a look at y units. Y units. Oh yeah, moving up and down y. So if I said x comes first, x, y goes to x, y plus c. We say x dash is equal to x, y dash is equal to y plus c, x equals x dash, y equals y dash minus c. Now you might think, hang on a sec, that's minus. But if we have an equation y equals f of x, we replace y with y minus c equals f of x stays the same. When I bring that c to the other side, I get y equals f of x plus c. So that's a translation up C units. And like I said, in terms of matrices, you just keep the same value, like plus whatever C is if you want to move it up C. Now I'm just going to write it in terms of a matrix so that you know. Okay, let's start here. X, Y dash equals A, 0, 0, B, X, Y, plus C, D. So A is a dilation factor A from the y-axis. In terms of function notation, that is f of x on A, because when we dilate from the y-axis, this is the reciprocal in function notation. In terms of image mapping, x, y, if I want to dilate factor A from the y-axis, all of my x values are multiplied by A, so I get ax, y. If we want to write that in terms of image equations, we say x dash is ax, y dash is y. So we get x equals x dash on A, we get y equals y dash. And of course we now replace our x's with x on A and our y's with y. So that's why we get y equals f of x on A. In terms of function notation, they click together. And of course, we just said that that's a dilation factor A from the y-axis. Okay, B, well, that's a dilation factor B from the x-axis, which it is B times f of x. In image equations, x, y becomes, now if I multiply by b, I'm multiplying the y value by b, so I get y, x, by. In terms of function notation, x dash equals x, y dash is equal to by, x equals x dash, y dash y is equal to y dash on b. So if y equals f of x, we get y dash, or we get y on b is equal to f of x. If I multiply the b across, I get y equals b times f of x, which as you can see in function notation, that's exactly the same. And that's a dilation factor b from the x-axis. Now if we want to reflect in x or y, if we want to reflect in the y-axis, A is negative, and if we want to reflect in the x-axis, B is negative. If I want to translate C units right, so we put a C up here, but that's f of x minus C in terms of function notation. In terms of images, I'd have x, y becomes, x plus C, because I want to move it to the right. The point, I want to move it to the right, C units. And y, so our image, x dash equals x plus C, y dash is equal to y. From there, we get x is x dash minus C, and y equals y dash. If y equals f of x, we're going to get y is equal to f of x minus C, which means to translate it C units right. So we know that's right. And lastly, if I want to translate up and down, and likewise, like if that was minus, it just moves it left. If I want to translate d units up, well, our x, y, our x would stay the same, but in this case our y would be plus d. So x dash equals x, y dash equals y plus d. From there we get y equals y dash minus d, x equals x dash. If y equals f of x, then we're going to get y minus d equals f of x. Therefore, y is equal to f of x plus d, which we know is a translation up d units. That's in function notation, image notation, and then here it is in matrix notation. Okay, so let's have a look at this equation. We can do it a few ways. It says the transformation t, all real numbers from the real number set. I have x, y. Now we know this is a dilation 2 from the y-axis, and that's a dilation 1/3 from the x-axis. So we can do it function notation wise. If it's a third from the x-axis, it's 1/3 times f, and we'd usually say f of x. Because it's 2 from the y-axis, it's f of x on 2. Okay, so if we put that into this equation, we're going to get 1/3 times 3 sine. Remember, replace x with x on 2. So 2 x on 2 plus pi on 4. They're going to cancel each other out, so I just get sine. When I multiply 2 times x on 2, I just get x. When I multiply 2 times pi on 4, I get 2 pi on 4, which is pi on 2. So that's our equation, sine x plus pi on 2. Okay, what's sine x plus pi on 2? Is it any of them? Have I stuffed something up? No, so if I dilate it half from the y-axis. Okay, so sine x plus pi on 2, that's the same, that's going to be positive, but it's exactly the same as cos of x, because we know sine of x minus pi on 2 is equal to cos x because it's in the first quadrant. So sine of x plus pi on 2, that's also the same as cos of x, because in the second quadrant we know that sine is positive, and we know when it's off the y-axis that it's the same as cos x, so it's going to just be y equals cos x. You can check it. Sine of x plus pi on 2, does it equal cos x? You just sketch it. Sine of x plus pi divided by 2, is that equal to cos x? You can see there, they're exactly the same graph. So if you're unsure and you got this answer, and you go, oh, hang on a sec, it's not here, sketch that graph, sketch all these graphs and see which one looks exactly the same. Oh, I didn't do it any other way. Okay, so that was doing it with function notation. We can also expand it out. So x equals 2x, x dash equals 2x, y dash equals y on 3. Therefore, x equals x dash on 2, y equals y dash on, times 3. Because when we times that 3 across, y equals 3y dash. If I sub that into the equation, I get 3y, because I'm replacing y with 3y. So 3y equals 3 sine. I replace x with x on 2, so 2x on 2 plus pi on 4. When I divide that 3 across, they disappear. So I get sine. When I multiply that 2 in, I just get x plus pi on 2, and of course we know that that's the same as cos of x because we just went through that. So that's matrix notation, telling us how to work it out. Okay, the graph of a function obtained from the graph of the function g with a rule that by reflection in the x-axis. Okay, so if we reflect it in the x-axis, that's negative g of x, which is negative root 2x minus 5, followed by a dilation from the y-axis by a factor of half. Now, because it's a half and it's from the y-axis, we've got to say g of, now because it's a half, the reciprocal is 2x, so I'd have negative 2 times 2x minus 5, negative root 4x minus 5, which is this answer here. If we wanted to do it in matrix notation, we could say a reflection in the x-axis followed by a dilation of half, so a half from the y-axis reflected in the x-axis, 0, 0, x, y, x dash, y dash. Okay, so I get x dash equals a half x, y dash equals negative y. From here, I get x equals 2x dash, y equals negative y dash. When we sub into the equation, negative y equals root 2. I've got to replace x with 2x minus 5. We get y equals negative. When I bring that negative across to the other side, root 4x minus 5. So we get the same equation as before. Now let's do it. A reflection in the x-axis, so x, y. If I reflect it in the x-axis, I change my y value, so negative y, followed by a dilation factor half from the y-axis. So that means I halve all of my x values, so I get x onto negative y. So therefore, x dash is equal to x on 2, y dash is equal to negative y, x is equal to 2x dash, y is equal to negative y dash. Same thing as before, when we sub it in, we get negative y is equal to 2x minus 5. Excuse me. Y equals negative 4x minus 5. So either any way we get the same answer, which is always nice. Okay. This one, it's a bit tricky because it says the transformation this maps the graph of the function f to the graph of y equals x squared. So it's already had this applied to it to get to this. We want to go backwards. All right. So usually we would expand this out. We'd say x dash is equal to x plus 5, y dash is equal to negative y. Then we would transpose it, but we don't want to transpose it because we've already got what it became, but we want to know what it was originally because it says it maps the function of f to the graph of this. So we want to go, it says the rule of f is, so we want to work backwards. So in this case here, we sub these into the equation without transposing them. So I get negative y is equal to x plus 5 squared. And then we get y is equal to negative x plus 5 squared. So that was our original equation, because once I apply these transformations to it, I'll end up with this value, this function. So because we're working backwards, if we wanted to, we could say it's been reflected in the x-axis. So if we reflect y equals x squared in the x-axis, we get y equals negative x squared. And it's been translated 5 units to the right already. So we want to translate it 5 units to the left. So here, I should have written negative f of x, gives us that. If I want to translate it 5 units to the left, because it's been moved 5 to the right to get to here, so if I want to go back the other way, it's f of x plus 5, which is y equals negative x plus 5, all squared, which is what we got either way. Okay, this next function, this was a graph. This was a couple of years ago, but anyway, it says find the period and range of f. So the period is 2 pi on a half, which is 4 pi. The range, our center is at pi, and we've got to go up 2 and down 2. So we've got pi minus 2 and pi plus 2. State the rule for the derivative function f dash x. Let's clear this. Okay, so it was 2 cos x divided by 2 plus pi. So that's f of x. If I want to find the derivative, just to check and make sure I haven't stuffed anything up, d dx of f of x. So it's going to come in handy, I'm sure, later. Okay, so negative sine x on 2. Of course, we know pi, when we derive it, becomes nothing. To derive cos, it's negative sine, and we've got to bring the coefficient of x out to the front and multiply it. So a half of 2 is negative 1. Find the equation of the tangent to the graph at x equals pi. It's a 1 marker. Like I said, I want to find the equation of the tangent, interactive calculation, line, tan line at x equals pi. Okay, negative x plus 2 pi. Now don't forget, it's y equals. Apparently, I read one of the reports a few years ago, and kids just wrote negative x plus 2 pi. That's not the equation. Okay, find the equations of the tangents of the graph between 0 to 8 pi for that graph that have a gradient of 1. So if it's a gradient, we know f dash of x has to equal 1. Therefore, so let's solve that. F dash of x, d dx f of x equals 1. Now the only problem with this, it's going to give us a general solution, but we want it between 0 and 8 pi. So 0 is less than or equal to x, which is less than or equal to 8 pi. Oops, I forgot. Okay, 3 pi, 7 pi. So there's 2 times when the gradient equals 1. X equals 3 pi, 7 pi. When x equals 3 pi, when x equals 7 pi. Now we've pretty much just done the same question before, but before we had pi, so let's do 3 pi, x minus 2 pi. And 7 pi, x minus 6 pi. So that's those two equations. Okay, the rule of f dash can be obtained by transforming the rule of from f. So we can go from this to this by using some transformations. And here is our transformation. So let's expand it out. X is equal to x minus pi. So x dash is equal to x minus pi. Y is equal to ay plus b. Okay, so let's transpose them. So we get x equals x dash plus pi. Y is equal to y dash minus b on a. So when we apply these transformations to the original function, we should end up we can end up with the other function, the derivative function. So let's do it. We know that y equals 2 cos x on 2. No. Oh, yeah, it is x on 2. Plus pi. So let's put it in. Y minus b on a equals 2 cos x plus pi on 2 plus pi. Now we want to make that the sine graph. We want it to become negative sine of x on 2. Yeah, that's it. Okay, so let's multiply the a across. So I get y minus b is equal to 2a cos x plus pi on 2 plus pi a. And then I get y equals 2a cos x plus pi on 2 plus pi a plus b. Okay, so somehow that has to be the same as that graph. Now there's got to be a relationship between cos of x plus pi on 2 and sine of x on 2. So let's see. What was it? Cos of x plus pi divided by 2 and sine of x divided by 2. Okay, so cos of x plus 2 isn't equal to sine of x on 2, but I think it's equal to negative. So we sketch it now. If we put the red one back. So cos of x plus pi on 2 is equal to negative sine of x on 2. So then we can say from here that is the same as y equals negative 2a sine of x on 2 plus pi a plus b. Now, we know that negative we know that 2a, because our equation that we want it to become is negative sine x on 2. We know that 2a has to equal 1, so therefore a has to equal a half. And we know that there is no value added on, so pi a plus b has to equal 0. We know a is a half, so pi on 2 plus b has to equal 0, so therefore b has to equal negative pi on 2. So, if we were to, what are we going to say here? We want to dilate 1/2 from the x-axis, and we're going to translate it left pi, and then up, down, down pi on 2, because of the negative pi on 2. So if we did that to this graph, like if we translate it, that's f of, because it's minus pi, that's going to move it to the left, so that'll be x plus pi. If we put a half out the front, and then if we move it down, pi on 2, that would bring the original graph, 2 cos x on 2 plus pi. So let's try it. What did we say? A half x plus pi minus pi on 2. 1/2 f of x. Now I said x plus pi, and then minus pi divided by 2. So you can see that's our red graph, that's our blue graph, and f of x is our original graph. So once I apply those transformations to it, I end up with exactly the same graph. So we must have got it right. Find the values of x such that f of x is equal to 2 times f of f dash of x plus pi. Okay, so you can just do that on the cas. So f of x equals 2 times f dash of x, which is fx plus pi. Solve. Now, of course, it's going to give us a general solution, but if we go 0 is less than or equal to x, which is less than or equal to 8 pi. Okay, 3 pi and 2, 7 pi and 2, 11 pi and 2, 15 pi and 2. So I guess you just write them down. Okay, last one. The transformation t such that r from just means x and y values from the real number set. Okay, this is a reflection in the y-axis, dilated 2 from the x-axis, translated right 1 and down 2. Okay, so I'm just going to transpose this equation. I get 2y is equal to x minus 3, so I get y equals x on 2 minus 3 on 2. So let's do, we've got to do our dilations first because they are first here. So if I reflect it in the y-axis, so that's step 1. If I reflect it in the y-axis, I replace x with negative x. So that's negative f of x. No, that's f of negative x. So that will give me negative x on 2 minus 3 on 2. Dilated 2 from the x-axis, so that's 2 times f of x, which is going to be negative x minus 3. Then if I translate it right 1, I get f of x minus 1, so that becomes minus x minus 1 minus 3, which is minus x plus 1 minus 3 minus x minus 2. That's y, of course. And then down 2 minus x minus 4. Okay, so if we bring the 4 to the other side, and I get negative x minus y, so we bring that over and bring that over. So I reckon it's this thing here. Okay, we did it with function notation. Now let's try it with matrices. Okay, so let's expand it out. So x dash is equal to negative x plus 1. Y dash is equal to 2y minus 2. What do we get here? X is equal to 1 minus x dash. Y is equal to y dash plus 2 on 2. If we put that into the equation, we get 1 minus x minus 2 times y plus 2 on 2 is equal to 3. They cancel. So we get 1 minus x minus y minus 2 is equal to 3. I get minus x minus y. 1 minus 2 is minus 1. When I bring it to the other side, it becomes plus 1. So I get 4. So that's the same as what we got before. If we want to quickly do it in the other notation. Okay, we know... Oh, stupid thing, I don't know why it's doing that. Okay, so that's so x, y, that would go to, that's a reflection in the y-axis. So that makes all my x values negative. And that is a dilation factor 2 from the x-axis, so that would become 2y. And then I want to move all of my x values right one, so that'll become negative x plus 1. And I want to move all of my y values down 2, so 2y minus 2. So we get x dash is equal to negative x plus 1, y dash is equal to 2y minus 2, x is equal to 1 minus x dash, y is equal to y plus 2 on 2. Then when we sub them into the equation, x is 1 minus x dash minus 2, y plus 2 on 2 equals 3. Looks familiar. 1 minus x dash minus y minus 2 equals 3. Get rid of that dash. Once you sub it in, you can get rid of the dash. 1 minus 2 is minus 1. Bring it to the side, plus 1. Minus x minus y equals 4. So we've gone through every question using different methods. So hopefully this should make sense to you, maybe. I hope so. Yeah. Good luck with that.